the online lecture. So hello everyone. I am Annie Cazenave. I am the Director for Earth Science at the International Space Science Institute in Bern, Switzerland. And I have the great pleasure to welcome today our speaker, Josh Willis. I will first explain what is this series of what we call game changer online seminars. In fact, it was an initiative of our of the EC director, Tilman Spohn. So since the last summer, he decided to launch a new series of online seminars on the topic of how space missions have changed our view of initially it was of the solar system. So for several weeks, all lectures have been dedicated to solar system science. And later on, a number of new lectures have been devoted to astrophysics, cosmology, etc. And we decided that as of this new year, we extend this initiative to Earth observation. So today, it is the first lecture in this new discipline, Earth observation, game changer for Earth science. And I have the great pleasure to welcome Josh Willis, the first speaker of this new series. So let me introduce Josh by a few words. So Josh Willis is a climate scientist at NASA Jet Propulsion Laboratory in California. He received his PhD in oceanography in 2004 from the Scripps Institution of Oceanography. And after that, he worked at JPL since 2004. So his research deals with ocean circulation and sea level using satellite altimetry and Argo data and other data and modeling. He is also studying the contribution of ocean warming and land ice melt to sea level rise. And more generally, he is studying the role of the ocean in climate change. So over the past 20 years, Josh has been a project scientist of the JSON-1, JSON-2, JSON-3 mission. So JSON-1 launched in 2002 and JSON-2 and JSON-3 in 2008 and 2016. And he is also the project scientist of the recently launched JSON-CS, or also called Sentinel-6 mission, which is the successor of the JSON series. Since 2015, Josh has been the principal investigator on the NASA mission Ocean Melting Greenland, a 6-year-long airborne mission. And I think your background, Josh, is from this project. So this project is dedicated to understand how the ocean are driving ice loss in Greenland. He is also co-chair of the Ocean Surface Topography Science team. In 2009, he received the Presidential Early Career Award for Scientists and Engineers. And he has also a long list of other awards that I will not comment now. So I would like to finish to just tell you that Josh is also a pretty funny guy. He has been known to dress up as Elvis Presley and sing songs about climate change, and also dreams of becoming a stand-up comedian someday. He has not yet quit his day job at GPL on satellite altimetry, but maybe at the end of this presentation, maybe Josh, you will sing us a song about climate change or something else.
Oh, we'll see if everyone behaves.
Okay, so Josh, it's up to you for 40-45 minutes, and after that we will have a session question and answers. So please.
Okay, thank you so much, Annie, for that very generous introduction. And thank you so much for the invitation to be here. It's really exciting to see so many friendly faces in the attendee list, and really exciting to speak to the International Space Science Institute. I've looked back through some of the past speakers, and it's really quite an amazing lineup. So I'm really honored to be here. Well, so the title of my talk, Reshaping the Earth, really comes from the fact that we're doing a sort of enormous experiment with our planet right now. And as I know that a lot of the lectures in this series so far have really been outward looking, you know, what we learn about the solar system and beyond from our spaceborne assets and other things. And it is the Institute of Space Science, but I think what I'm hoping, I think what Annie would like to do with this this talk and hopefully some additional ones is to begin to look inward. Of course, we look back at the Earth from space and learn a tremendous amount about what's going on with our planet. And I wanted to start with this very simple picture of the Earth. This is a picture not taken by one of the satellites that I'm going to talk about very much, but it's taken by the EPIC camera, which looks back at the Earth from the point about halfway between the Earth and the sun. And I find these pictures really stunning. I've really enjoyed watching them, watching what this satellite is producing, because it produces this really incredible view of the Earth. You can see the moon just over the Earth's shoulder in this shot. And it's a reminder that we really are, you know, one of the most important things we do with our satellites and our spaceborne science assets is try and understand the planet that we live on. This planet, which is changing so rapidly because of what we're doing to the Earth's climate, is our only home, and the study of it is really one of the most important things we can do scientifically from space. Now, as Annie said, I also like to kid a little bit, and so before I get too serious and talk about climate change, you know, one of the things that I think is important as we talk about serious subjects is to be willing to sort of make fun of ourselves. And so I'm going to show you this short video, hopefully this will work, of what happened at the launch of the current reference mission for these sea level satellites, Jason 3. This was in 2016, and it was back, if you might recall, that SpaceX, which was produced the launch vehicle that we sent Jason 3 to space on. They were at the time trying to land one of the rockets on this barge, this floating barge, for the first time. And this is what happened at the launch of Jason 3. We'll see if this works.
We'll take questions now, and we'll start right here at the front.
Can or will you guys care to comment on the launch vehicle?
I will say that we're excited to get a ride to space, and we hope SpaceX breaks a leg.
Yes, so there you go. Well, so, you know, not everything that we try to do turns out as planned. And you might argue, actually, that the warming of our Earth is one of those things, one of those moments that, as we look back in history and we reflect on how our Earth is changing, where we say, maybe we should have thought about that a little bit more. Of course, one of the most important things that's happening on our planet at the moment is the change in the climate that's happening as a result of human released greenhouse gases. Yeah, by the way, if you're interested in that video, you can Google break a leg SpaceX and you can find the video on on YouTube. But these greenhouse gases are warming the Earth. And you can see from this recent estimate of temperature, which is produced actually at NASA, that NASA as an agency, and I know and many space agencies around the planet, spend a very large portion of their budgets studying the home planet. So although we often think of space science as looking outward, really a lot of it already does look back towards the Earth and try and help us understand how the climate's changing and what that means for the future. So the Earth's temperature has gone up by a little more than 1 degree Celsius in the last 150 years. It's one of the clearest signals that you can see in terms of the entire planet. And the cause of this is not really in doubt. If we look back at the history of carbon dioxide in the atmosphere, we can see for the last 500,000 years, carbon dioxide has gone down and up and down and up. And this is the cycle of the ice ages, where you have a glacial period. It gets very cold on the planet when CO2 is low in the atmosphere. As CO2 comes back up, the planet warms up. There's this cycle that's been going on. And what's happened in the last 150 years is that we've broken out of that cycle of warm and cold, this cycle of the ice ages, and we've forced the carbon dioxide in the atmosphere above 400 parts per million. And so this is really radically changing how our planet is, how our planet's climate is playing out. And we'll see some of the consequences of that in this talk. But of course, the consequences are many. You know, there's been this debate over whether we should call this global warming or climate change. And of course, the short answer is it's both. The planet is definitely warming, as you saw from that previous graph, but the climate is changing as well. This includes things like sea level rise, like the changing of the seasons, the changes in rainfall, drought, storminess. So climate change includes all of that, and it's really affecting the planet as a whole. Now, how do we know that carbon dioxide over the last 500,000 years has been going up and down, and that it's higher now than any time in millions of years? Well, we don't know that from satellites, but we know that from the ice that's been left behind during these ice ages. Whenever you have a place on the Earth where the snow doesn't melt completely in the summer, that snow accumulates year on year. And every year, as the new snow falls, it traps small bubbles of air in the ice. And if you find a pristine location, you can actually drill down through this ice and recover a record of the past atmospheres. And that's one of the ways that we know that carbon dioxide has gone up and down, by looking in the great ice sheets in Greenland and Antarctica. And you can actually also tell separately how the surface temperatures have changed over time. So you can get both the composition of the atmosphere and the surface temperature, and you can really get a picture of how the climate has been going through this natural cycle for hundreds of thousands of years. And now we've pushed the Earth into a completely different regime. And there, as I said at the beginning, this includes not just global warming, but climate change. And climate change encompasses a large array of things, such as the disappearance of the sea ice in the Arctic. If you look at the Arctic in summertime, the sea ice retreats. Of course, remember the Arctic is an ocean. So this is all ice that is floating on water, and sea ice is ice that freezes out of the water, out of the ocean water. And if you look in the summertime, in the wintertime, the ice expands to cover most of the Arctic, but in the summertime, it melts and retreats. But if you look in the last several decades, the area over which the sea ice exists in the summer is getting smaller and smaller and smaller. And in fact, since the late 1970s or early 1980s, the area has decreased by about a factor of 2 over time. And in fact, the amount of thick ice which survives over the winter is getting smaller and smaller as well. So the overall thickness of the ice is shrinking. And that means the volume of sea ice in the Arctic has shrunk by about a factor of 4 since we really began keeping records in the last 40 years or so. So this is one of the impacts of that warming. Of course, the Arctic is warming faster than most other places on the planet, and so it's feeling the heat even more. But it's a reminder that the Earth is changing, not just in the sense that it's warming up, but it's changing in all sorts of different ways. And in fact, ice all around the planet is melting. If you look at glaciers anywhere on the planet, more than 90% of all the glaciers everywhere are in retreat. Very infrequently, you have these things called surge glaciers where they sort of cough up a bunch of ice and have speed up and slow down over a cycle of 10 years or more. But almost all glaciers everywhere in the planet are retreating, much like this one in Alaska. And you've probably all seen photographs like this where a glacier filled a giant fjord, and there's a photograph of it from the 1940s or even earlier in some cases. And if you go back today, the glaciers retreated miles into this fjord and shrunk. So ice everywhere on the planet is melting, and the consequences of this are being felt across the globe. In addition, in Antarctica, the giant, the frozen giant, I like to call it, at the southern part of the planet, ice is melting as well, and the ice there is actually a combination of different kinds of ice. There's ice on land, which makes up the whole ice sheet. That ice flows off the land into the ocean in the form of glaciers. And then there's this floating ice that's formed when the glaciers dump the ice into the ocean. And this is called an ice shelf. And what we know from looking at this is an older collapse of an ice shelf. But on the left-hand side is a satellite picture of the Larsen B ice shelf just before its collapse. And if you look carefully, so the white part here is all this giant pancake of floating ice. And this ice began to have water form on the top, these melt pools. So you can see these kind of dark melt pools that are holding this water. We know now also that the water temperature underneath the ice shelf, remember this is a layer of ice floating above a layer of water, and then the bed of the ocean is below that. And so the water beneath the ocean was warmer as well. And these things together caused this ice shelf to collapse. And the subsequent satellite photograph a month or two later shows that this enormous section has splintered and fractured, and the sort of light blue color here is ice that's just sort of what's called a melange. It's sort of just a floating mess of ice, and these huge icebergs have broken off. And this is actually a process we've seen repeated over and over again in Antarctica since this time. And what's interesting to me is that oceanographers have since gone back and drilled ice cores underneath or sediment cores underneath where the ice shelf used to be. And they found that the ice shelf was more than 10,000 years old, which means that it's stretched back to the last ice age. And that means that this change, this loss of this ice shelf is something that is unprecedented during human existence. So these ice ages have come and gone. But since the end of the last ice age, 20,000 years ago, this ice shelf has remained. And it's only the warming that's happened in the last 100 years that's beginning to cause these ice shelves to break up. And of course, after the ice shelf breaks up, this big pancake of ice was actually holding back some of the glaciers. And it's common for these glaciers to speed up and dump more ice in the ocean, which drives sea levels higher as well. So we're watching ice, as I said, melt across the planet, and we have another satellite which tells us a lot about how this happens, and that's the GRACE satellites, or now the GRACE follow-on satellites. And this is a pair of satellites that literally chase each other around the ocean, around the planet. And whenever they go over something heavy, the leading satellite speeds up just a little bit. The pull of gravity causes it to accelerate. And as the second one eventually follows, it catches up a little bit. And by measuring the distance between these two satellites very accurately, we can actually figure out the mass of the thing that they're flying over. And if we look at the mass of the great ice sheets in Greenland and Antarctica, they're both disappearing. I like to say they're both on Jenny Craig's diet plan. Greenland has lost more than 4 trillion tons since this set of satellites started flying in 2002. This graph's a little old, but it continues, the loss continues. And if you look at the places where Greenland is losing ice, it's losing ice mostly around the edges, where the glaciers are in direct contact with ocean waters. I'm not going to talk too much about my other mission today, Oceans Melting Greenland, or OMG for short. But if you Google OMG NASA, you can learn all about it. As Annie said at the beginning, this picture from behind me was taken out the window of an airplane that we use to fly around in Greenland and measure the oceans to try and understand how the oceans are contributing to this ice loss process. So we're watching the ice sheets disappear from space. We're watching the sea ice disappear. The ice shelves are retreating. And altogether, this paints a very clear picture of how the Earth is changing in a warming climate. Now, every global warming talk, and in case you haven't figured it out by now, this is a talk about climate change and global warming, has a slide like this. The way global warming works is that the most important energy for our climate system actually comes from the sun. So most of the energy from the sun comes in the form of visible light. It goes right through the atmosphere. The air is transmissive to that visible light. It warms the surface of the Earth. And then the warm surface of the Earth radiates the energy back out into space. But the energy coming from the Earth actually exists mostly in a different wavelength. It's a different kind of energy. So it's visible light mostly coming in, but going out, it's by and large infrared radiation. So if you've ever played around with an infrared camera and you can see the heat coming off of people, this is the energy that's trying to get back out to space from the Earth. And when the climate is in balance, the amount of energy coming in equals the amount of energy going out. But as we've changed the composition of the atmosphere on this planet, the amount of energy trying to get back out is being reduced. So carbon dioxide and other greenhouse gases, they absorb this outgoing energy and they warm up the planet. So they trap this extra heat on the Earth, and the Earth warms as a result. Now, the question is, what happens to most of that heat? Where does most of that heat go? And I know a lot of my OSTST colleagues are on this call, so I'm sure they all know the answer already, and they're sitting in their homes going, I know. If I could call on you and see you, I totally would. But here we are on Zoom, having a good time, hopefully. So what happens to that heat? Where does it go? Well, over 90% of the heat trapped by greenhouse gases that we've added to the atmosphere is actually warming the oceans. And this is an old number, but it's been recalculated many times. And it's really 90 or 95% of the heat trapped by the extra greenhouse gases is warming the oceans. And so that graph that I showed you at the very beginning of the talk of the rising temperatures of the Earth, that the energy required to increase the atmospheric temperature only counts for about 2% of the total heat trapped on the planet. So we think of global warming as happening to the atmosphere and happening to the ice, but really global warming is happening by and large to the oceans. That's an incredibly important fact. And it's one of the reasons why not Arthur C. Clarke, but it's one of the reasons why folks have argued that we should really call our planet ocean instead of Earth, right? More than 2/3 of our planet is covered by water, covered by oceans. And so in a way, we called it Earth, but really we named it the wrong thing. It's really ocean. And the oceans have an enormous role to play in climate change and global warming, partly because of this extra heat that they absorb. And also because one of the consequences of that extra heat is the rising of the oceans. As water warms up, it expands. This is about 1/3 of modern day sea level rise. But of course, I just spent all this time showing you these glaciers melting, the ice sheets losing mass. Together, those things are the other 2/3 of modern day sea level rise. And there's small contributions from things like storage on land and other things, but by and large, most of sea level rise is caused by the warming of the oceans combined with the melting of the glaciers and ice sheets. And so in a lot of ways, the oceans are responding to climate change in the most profound way. And the rising of the oceans is really our clearest indicator of just how much humans are changing the planet's climate. Now, if we look back at the history of sea level rise, we have a few indicators, a few of these sort of detective stories, kind of like the ice cores that I talked about earlier. These are places where we can drill down into the sediment and actually look at how sea level has changed over thousands of years. And this is from a single spot in North Carolina, where they were able to find an area where the tides are very small and the land is lifting up. And so by looking at a very specific species of little critters that live in the ocean in a very narrow range of the tidal band, they were actually able to reconstruct sea level with an incredible accuracy back more than 2,000 years. And what they found was that for 2,000 years, almost entirely, sea levels were very stable. During the medieval warm period, the so-called medieval warm period, starting about 1000 AD, there was a period of rising sea levels, very gradual rising sea levels. And in the Little Ice Age, the period just before the Industrial Revolution, maybe there's a little bit of falling sea levels, but by and large, from the year 0 to the year 1800, sea level stayed very stable. But since that time, sea levels have gone up very quickly, and the rising of the oceans has become one of the most profound changes that our planet has seen in the last 150 years. And it doesn't start until the Industrial Revolution. So to me, this is one of the most clear pieces of evidence that the changes that we're seeing now are something that are unprecedented in human history, and that they're related to this rapid increase in carbon dioxide that we've created in the Earth's atmosphere. Now, finally, I know this is the International Space Science Institute, so I'm going to get back to our satellites and our sea level satellites, which are really the focus of this talk. And our altimeter satellites, which I'll talk a little bit more about the history of in a second, beginning with TOPEX Poseidon, which was launched in 1992, and continuing on through Jason-1, Jason-2, Jason-3, and the just launched Sentinel-6 Michael Freilich satellite. These satellites were designed specifically to measure the height of the ocean as accurately as possible. And this tells oceanographers a wide variety of things, but one of the most important things it tells us is how the oceans are rising and how quickly they've been rising ever since the early 1990s. And what you see, this is a plot from Steve Neerum, who I think is on. You'll see it again, as well as a few other of his slides that I borrowed. Thank you, Steve. This shows the rise in the oceans for the last 3 decades. And what you can see is that this little blue line is actually not a straight line anymore. It's a quadratic fit. And there is a slight acceleration in the rate of global sea level rise. You can also see every year sea levels go up and down about 1 centimeter globally. This is due to the exchange of water back and forth between the oceans and the land. There's more land in the northern hemisphere, so this seasonal cycle is locked in with the northern hemisphere. And also every once in a while, there's a big El Nino or La Nina, which changes that balance of water going back and forth between the ocean and the land, and you see a weird little missing bump or an extra deep dip from a La Nina. But this is telling us an enormous amount of information. And of course, it's very important because 200 million people around the globe live in areas that will be affected by sea level rise or regularly flooded by the year 2100. And whenever you see a projection like this, counting people and counting sea level rise, one thing to keep in mind is that we're really not very good at predicting future sea level rise right now. And by and large, most of these estimates are probably too low. As we learn more and more about how the ice sheets are reacting to the warming climate, almost always we wind up revising our predictions of future sea level rise in the upward direction. So it could be actually higher, and even more people are affected by sea level rise in the years to come. Now, someone asked me to explain the TOPEX and JSON acronyms I saw in the chat. I'll talk a little bit more about those as we go along. TOPEX, which was the first of our sea level missions to be incredibly precise and able to measure the accuracy of the ocean in a single spot, to within a few centimeters, is actually not really an acronym. It stands for Topographic Experiment. So TOP from topography, meaning the shape of the ocean surface, and X for experiment. And the JSON missions were actually named in conjunction with the Argo program, which is a program which puts floats throughout the ocean, much like the ocean's weather balloons. They tell us the temperature and salinity of the oceans in the upper half all around the planet. And so JSON was chosen because of Jason and the Argonauts, and the JSON missions ever since have been subsequently named to follow on. And I'll talk a little bit more about the recent one, Sentinel-6, a little later on. So let's talk about how these satellites work. In a lot of ways, this is one of the simplest, clearest things we can measure about the planet. It's a radar satellite, which means that it can see through clouds and most weather. And essentially, the satellite has a radar dish on the bottom, and it bounces a radar signal off the surface of the ocean. Traditional satellites, when the radar beam hits the ocean, it has an area of a diameter of 5 or 10 kilometers that returns signal back to the satellite. That means it's averaging over this large area. So it's averaging over all the waves and things like that affect the surface. The signal comes back to the satellite, and we measure how long it takes to go down and come back up. So it's a very simple measurement. And you divide by the speed of light, and you get the distance between the satellite and the ocean surface. And of course, there are a lot of other things that we need to measure to correct for its travel time and things like that. But by and large, that's how the satellite works. Now, you need one more piece of information in order to get the height of the ocean, and that's where the satellite is. And the satellites, in addition to the radar, they have 3 different positioning systems that help us understand exactly where the satellite is. And with those 2 pieces of information, you can get the height of the ocean. So the satellites are actually kind of fundamentally very simple. They measure how far away the ocean is. They measure their own position. And then with that, you can tell the height of the ocean to within a few centimeters once per second as they fly around the planet collecting data. And you can read more about the satellites if you just look for, there's the sealevel.jpl.nasa.gov site, and all of the agencies, of course. NASA has been collaborating with CNES and more recently NOAA, EUMETSAT, and ESA to build this series of satellites to study the oceans. But that's the basics of how they work. And, you know, as I've been kind of hinting at this as we go along, this is really one of the most fundamental measures we have of how our climate is changing. So as CO2 rises in the atmosphere, sea levels increase around the planet, and it's really a direct effect because it includes both the warming of the waters, which cause thermal expansion and the waters to rise, sea levels to rise, and the melting of the glaciers and ice sheets together. And so it's sort of the most integrated measure we have of just how humans are changing the climate. And you'll notice that, remember I showed you the graph of the surface temperature warming over time. It was very bumpy. There's all kinds of internal variability and natural cycles that affect that curve, but this curve is very smooth. You have to get out your magnifying glass to really see the interannual changes. They're there, but they're a lot smaller than the global rise that we've seen in the last 30 years. Now, I'm going to borrow a few more slides from Steve Neeram. Thank you, Steve. Again, I mentioned this already, but the rate of rise is increasing. If you look in the early part of the record of sea level rise, the rate's about 2 millimeters per year. And by the recent decade or 2 decades, the rate of rise is more like 4 millimeters per year. So during the lifetime of these series of satellites, global sea level rise has doubled in its speed. And this is a really profound implication. How long will it take before it doubles again? What will the rate be for the next 50 years? These are all things that we are trying to figure out as fast as we can. Of course, the rate is not uniform either. It's becoming more uniform as we get a longer record, but natural cycles in the ocean move heat around and cause sea levels to go up in one place and down in another. And the global rise of the ocean happens sort of on top of that. And different places have different rates of rise. And some of that will also continue. The ice sheets actually have enough gravity to pull the water closer to them. The speed of rotation of the Earth changes as the ice melts. And so all these things, and in addition, the ocean circulation as well changes. And so all these things can cause sea levels to rise faster in some places than in others. And I really talked about the acceleration already. But I do think it's important to take a second and kind of appreciate the fact that as we look around for how fast sea levels are going to rise in the future, it's hard to tell. Some parts of the sea level rise signal we understand pretty well, like the thermal expansion part. How much heat is going to get trapped in the oceans over the next 20 years or 50 years or 100 years. This is something that's pretty well modeled, and you know, we argue about it, but the basic number is pretty well known. But how fast are the ice sheets going to melt? This is a problem that still plagues us as a community, and it's something we just really don't have a good handle on yet. And so in a sense, our altimeter records, which are measuring the rate of global sea level rise today and hopefully for the next decade and even longer, are really our best estimate of what's going to happen in the future right now. You know, this is an older set of projections from an old climate assessment, but it ranges from, you know, less than 50 centimeters by 2100 up to more than 200 centimeters by 2100. And of course, the difference between those two numbers is devastating. Hundreds of millions of people live in areas that would be affected differently by 50 centimeters of sea level rise than they would by 200 centimeters of sea level rise. And the short answer is we just still don't know where the rate of rise is going to fall, even for a given amount of warming. So our altimeters are really our best way right now of projecting the next 20 or 30 years of sea level rise, just on the basis of the fact that they have this clear acceleration term, which can now be measured and quantified and essentially extrapolated out at least over another decade or two. This is really our best estimate of the upcoming sea level rise. So I mentioned this a couple times already, so I won't spend too much time on it, but we started with TOPEX Poseidon in 1992. JASON 1, JASON 2, and JASON 3 were all launched in that over the course of the last 30 years. And what's been amazing is that each one of these has been able to overlap with its predecessor, and that's allowed us to get a really unbroken record with incredible accuracy over this entire time period. And of course, this is an older slide. It didn't have the Sentinel-6 name on it at the time, but the Sentinel-6 JASON CS mission, which is led by ESA and is part of the Copernicus program, and bears the Sentinel-6 name. This satellite is really remarkable because it's the satellite so nice we built it twice. In fact, there are two Sentinel-6 satellites. The first one was launched just a couple of months ago. The second one will be launched in 2025. And together they will extend our record of sea level another complete decade to 2040 or 2030, I forgot what year it is, to 2030 and possibly beyond. So it's a recognition of the importance of these satellites and the importance of maintaining this long record that the agencies have been willing to build two of them in order to extend the record an entire decade. Now, of course, I've talked a lot about sea level rise and global sea level rise, and that is one of the most important things that we measure with these satellites, but they tell us tons of other stuff too. The first one, TOPEX Poseidon, was actually launched in order to tell oceanographers about ocean currents and about the tides. And tides are one of the things that we've really sort of mastered in a lot of ways. There's still a lot to learn about tides, but the tidal signals in the ocean, of course, are a meter or more in many places. And we've been able to use these satellites because they have an exact repeat period to map out the tides and really predict the tides with an accuracy of just a centimeter or two everywhere in the world. And so the global ocean tide models, an early one of which is shown here, really tell us how sea levels rise and change and the oceans as a whole slosh around as part of the tidal cycle. And this was one of the first things we had to master with these satellites, because if you recall, I said we can observe the sea level to an accuracy of just a couple centimeters every second. But if you have a tidal signal that's going up and down 1 meter everywhere in the world, you have to really understand the tidal signal in order to be able to see all the other features. And that's something that we've really accomplished as a team in the last 3 decades. It's not just what we call the barotropic tides, or the tides that involve the movement of the full depth of the water column, but in fact, actually, there are also internal tides. Because the ocean is stratified, it's warm at the surface and cold down deep, you can actually get tides that propagate on the interface between the warm water at the surface and the cold water down below. In fact, you can see this was from an old paper by Richard Ray and Gary Mitchum showing the barotropic tides in red and the much smaller baroclinic tides. This is the tides that happen on that interface across the Hawaiian Ridge. So this is a track from the TOPEX data, and essentially what they did was look at the tidal signal in this track, and the barotropic tide is big because it involves the movement of the whole water column. It's kind of the whole ocean sloshing around, and the baroclinic tide, the tide on the interface, actually just happens locally right around the ridge as the water sloshes back and forth across the ridge. So there's all kinds of really exciting science that people have been doing for this last several decades. I've talked a lot about why the ocean changes its shape, it's rising. Of course, the shape of the ocean isn't just set by the oceanography or the tides. The pull of gravity plays an important role in the shape of the ocean. Whenever you have an island or something, the water actually bows up from the pull of gravity and sort of gets higher around the island. And this shape, which is defined by the Earth's gravity field, is called the geoid. And it's another thing that we learned very accurately over the course of taking sea level measurements for 30 years. And I should say here too, I'm talking about these reference missions, but there are a whole host of additional sea level satellites that have filled in a lot of the gaps, that have collected data in more places at higher latitudes and different times. And there's a whole host of these altimeters, and together they've given us an incredibly clear picture of the geoid, which is this change in the gravity field caused by usually changes in thickness of the Earth's crust, seamounts and things like that. There's a lot of things that go into the gravity field. But we've gotten a really clear picture of it over the oceans because we know the shape of the water so well. Now, I mentioned a second ago that this is an oceanographic mission. So whenever there's a current in the ocean, it tilts the sea surface. If a current lasts for more than a day and travels over more than a bunch of kilometers, then it actually causes what's called a geostrophic balance in the ocean. And when that happens, you have high water on the right of the current and low water on the left of the current. And so by looking at the troughs and ridges in the sea level, you can actually learn about the surface currents of the ocean. And that's something that we've been doing for a lot of decades as well. This dynamic topography, so if you remove the part of the sea level caused by the geoid, where the water's piling up around the land, then mostly what's left is the sea level that's related to these ocean currents. And these ocean currents, so this is a picture, this topography. I said it's high on the right, low on the left. That means the gradients of sea level, the derivatives of sea level, tell you the ocean currents. And so you can see where the contour lines are bunched up, like in the Kuroshio, which is the big current that goes off the coast of Japan, or the Gulf Stream, the current that goes off the east coast of the United States. The lines are bunched very close together. That means there's a very steep change across the sea level, across this current, and it's one of the things that we measure with the sea level satellites. And this is what the currents look like. If you go ahead and take the derivative of that field before, you can see these really fast currents off the eastern coasts of the continents. Now, the currents are something that we learn about not just in the big picture, but in real time as well. When we have many of these satellites together, giving us a very fine picture of the sea surface, we can actually look at currents in great detail. And this is incredibly important sometimes when disasters occur, like the Deepwater Oil Horizon spill, Deepwater Horizon oil spill, or the Fukushima disaster, the debris field is carried by the ocean currents, and measuring them from space is another very important aspect of what these satellites do. Now, I mentioned this already, but warm water expands and stands taller than cold water. That means the sea levels are also telling us about where the heat is in the ocean. That's important for things like predicting hurricane intensity. Hurricanes travel over warm spots in the ocean, and they tend to speed up and become more intense. So the satellites help us with hurricane forecasting. And of course, they help us learn about El Nino as well. I won't go into that one in too much detail because I want to get on to other things. But the El Ninos are huge changes in the heat in the Pacific Ocean. There's a redistribution of warm water from the Western Pacific to the Eastern Pacific. And when that happens in an El Nino, the sea level in the West drops sometimes by as much as 20 centimeters. It rises in the East by similar amounts. And the changing temperatures of the water then actually affect the weather. They affect the jet stream, which carries storms across the Pacific Ocean. And when the El Nino is this big, like couple of the largest two we've seen in the last 30 years, it can actually have implications for weather all around the planet. So when El Ninos are really large, they can have enormous effects on weather. And I'm going to skip the tides and talk a little bit about eddies. The ocean is full of little storms, which we see in the eddies in the ocean. These are like little swirls of current, sometimes that close on themselves and actually carry water from one place to another. They tend to propagate westward through the oceans, and using these altimeters, they look like either bumps or dips in the water, and you can actually track the eddies with enough satellites and study how they mix the oceans together as a whole. People also use altimeters to understand where the sharp gradients in temperature are. Whenever there's a very fast ocean current, I said it tends to be high on the right and low on the left in the Northern Hemisphere. That means it also tends to be warm on one side and stand taller, and cold on the other and stand shorter. And so that means that the satellites also tell us about temperature gradients in the ocean below the surface, and that's important for fisheries, which often tend to, often the biology kind of likes the sharp gradient, and so fishermen often will look for these eddies and try and fish around the edges of them for certain kinds of fish. So there's all sorts of uses for this. I'm going to skip ahead just a little bit because I'm running out of time. But the satellites also tell us about the weather around the ocean. Remember, I said earlier that the radar beam hits about a 5 or 10 kilometer area of the ocean, and the radar return comes back from that area. Well, by looking at how much return comes back versus how much gets scattered, you can learn about the wind over the ocean. And you can also learn about the wave heights. If you think about it for a second, a tall wave, a peak of a wave will get a return signal sooner than the trough of the wave. So looking at how the signal spreads out also tells us about the wave heights. So wind and wave heights over the ocean are also collected and actually used by forecasters to better understand marine weather and to validate forecasts of marine weather. And I'd be remiss if I didn't say something about the science team. Of course, all of this work that I'm showing you comes from a team of incredibly dedicated scientists and individuals, about 200 folks. We get together every year. At least we get together in person when there's not a global pandemic. And this group of people who've been working on this data set for many of them for their entire careers have really done an incredible job of bringing this data to life and using it for so many really amazing scientific purposes. Now, really quick, so that there's time for questions, we had a launch, I noted this year. It was very exciting. Again, we got a ride on SpaceX and a SpaceX rocket, and what was amazing about this one back in November was that this rocket actually, unlike the one I showed for Jason 3, it landed successfully, and it actually landed back at the rocket site where it took off. So we got to see the rocket take off on a very clear, gorgeous Southern California day, and we got to see it come back. Here's a little picture of it. Here's a little video of it coming back. You can actually see the rocket right there as it comes back down over the hill. And I'll play this little video for you. When the rocket comes back, it's going faster than the speed of sound. So there's a sonic boom that travels away from the rocket just after it lands. And so in this video, I actually captured the sonic boom. So here we go. We'll just play it. Oh, it's upside down. Anyway, listen. Yes. So that's actually not the rocket exploding. It's just the sonic boom from when it was coming back down through the air. Maybe I'll put this out somewhere right side up so you can watch me stutter when it happens. So this was the launch of Sentinel-6, our latest sea level satellite. It was named after Mike Freilich, the director of NASA Earth Science for most of the last decade, who very sadly passed away before he was able to watch the launch. But this mission was named after Mike, who was a great friend of the altimeter and member of the altimeter community, and oversaw the or participated very did a whole lot for getting this satellite and this mission off the ground and establishing the collaboration with ESA and the other partners. And so it was a big kind of emotional day on November 21st when it finally launched. And we're also excited to say it's producing good data. Some of the very first data has already been retrieved from the satellite. It looks fantastic, and it looks like it's going to carry on the legacy of the sea level satellites quite nicely. And now, just before I end, I want to say just a quick thank you to Lee Fu, who gave me a couple of slides for the SWAT mission. This is an upcoming mission that'll launch in 2022 and is really the next generation of these type of satellites. So one thing I didn't talk too much about is that these satellites, I said they look at an area of 5 to 10 kilometers of the ocean. Oh yeah, yeah, you're right. It was 2020. Sorry, Sentinel-6 launched last year. It's been a rough year. I forgot what year it was. But anyway, the SWAT mission will actually give us incredibly fine resolution over the oceans because it's a swath altimeter. So it'll use interferometry over the oceans to get down to as small an area of a few kilometers or 10 kilometers resolution. And so it'll paint a much clearer picture of the oceans. And of course, it's also going to measure water over land, which I didn't talk too much about with our previous altimeters, but SWOT will really produce an enormous amount of data on lakes and rivers over land, which I think will start to revolutionize the field of hydrology in much the same way that oceanography was revolutionized 30 years ago with the launch of TOPEX Poseidon and the other precision altimeters. So with that, I'm going to leave you with one last thing. Annie asked if, oh yeah, and Jerome says I should remind everyone that Sentinel-6 also has higher long track resolution. Although it's not a swath like SWAT, it will see clearer picture along the track. Annie asked if I would sing you a song, so I'm going to play you a video instead. I do like to communicate about climate change, and I really enjoy doing that. And so this is a little video that I put together. It's about 30 seconds, and then I'll take questions.
Hello there, little lady.
Say, what's climate?
Well, you curious little ankle biter. Climate is the generally prevailing weather conditions, including temperature, precipitation, humidity, wind, cloudiness, as a function of time throughout the year, composited over many years.
What?
Let me try something a little different.
Sunny on Sunday, high 73. Monday, rain was pouring down on me. Tuesday was cold, I almost froze my toes. Oh, what's it gonna be next week? Who knows? That's weather. Oh, that's the weather you got. But you take a bunch of weather and you average it together and you're doing the climate rock.
All right, there you go. If you want to watch the rest of that video, you can Google Climate Elvis and it should pop up. And I will end my talk there and take any questions that you might have. And thank you again, Annie, for having me so much.
Okay, thanks very much, George, for this fantastic presentation. I think everybody enjoyed listening to you. So it was really, yes, like Miora is saying, it was super. So I think we have time for a few questions. So I have to manage that. I propose that the participants who want to ask you a question raise their hand. So I see already several. Wow, a lot. So, so let's start by Rainer Rummel. So Rainer, I don't know if you can unmute and ask your question. Or maybe in the chat, I don't know. Est-ce que tu peux demander à Willy qui vienne m'aider là pour les questions parce que maybe Josh, can you stop sharing your screen?
Sure, how about that?
So we will see the participant, maybe.
There we go.
Okay, thank you. So there was a question by Rainer, but he's muted. So we move to the next one. I don't know the name, so I see just last name Frisch. Can you ask your question either in the chat or they are muted? You are muted. Hello? Okay, so the question.
Oh yes.
Okay, go ahead, please.
My question is whether or not there is any evidence that the galactic cosmic ray flux at the top of the atmosphere affects the cloud cover.
That's a great question. Yeah, and I think I actually don't know the answer to that question. I know folks study the cloud cover and what causes it, and of course clouds do continue to be something that make it more challenging to project what's happening in terms of climate change and global warming. But I think it's pretty definitive to say that we know the primary cause of the warming is from CO2 increase and greenhouse gas increases, and that other secondary effects are important, but the greenhouse gases are really the big dog when it comes to things like how much heat the Earth is absorbing, how much sea level rise we're getting, and so forth.
Okay, thanks. So the next question is Baptiste Rousseau. So can you ask your question? You can talk. You are unmuted. Okay, so I will read the question, or maybe Josh, you can read it. So the question
Yes.
is, okay.
Yes, beyond monitoring sea level and other measurements, is there any particular scientific or technical challenges in this field for the next few years with Jason and others? Yeah, absolutely. So one of the big technical things that we're trying to do is really see finer details in the ocean. And that'll be really big. That'll be a really big change with SWOT, but it's also important with Sentinel-6 because, of course, sea level rise, which happens all over the planet, matters most where we live, which is all along the coasts. And so this new generation of satellites has several aspects that will allow us to get sea level data closer to the coast and in finer detail. And that's really important because we have to, I know Annie's talked a lot about this and done some interesting work on it. We really have to connect the signals that we see in the open ocean with what's happening on the land where people live, because that's where the impacts really are. And so we think this generation of satellites, Sentinel-6 and eventually SWOT, will play a very important role in helping us connect the larger scale picture with the details of where we actually live.
Okay, thanks. So there is another question, by Hans Zinecker.
Yes. Hello, can you hear me?
Yes.
Yes.
Okay,
hi.
so I had two questions. One was about Envisat, I think, which is an ESA satellite. What did it contribute? And my other question was about El Nino, whether we can predict El Nino, because I'm an astronomer, so it might be important to understand for astronomy what causes the El Nino effect and whether it can be predicted in time.
Yeah, that's a great question. So Envisat helped us, two great questions. Envisat really helped us fill in the gaps between where our traditional reference altimeters fly. I didn't show the map of the spatial coverage of these altimeters, but at the equator, their ground tracks are about 300 kilometers apart. So that leaves a big gap where we need to fill in data. And missions like Envisat, ERS-1 and 2, the Sentinel-3 satellites more recently, all of these have helped us get a much clearer picture. And you really couldn't see things like the eddies that I talked about very briefly. You couldn't see those without the extra satellites. You really need more than just one to get that kind of detail. And of course, they're also higher latitude satellites. So they've extended our sea level measurements into places like the Arctic and Antarctica. In some cases, you can actually see between little cracks in the sea ice. So you can actually get a sense of what the oceans are doing, even in places where there's sea ice cover. So all of the other missions, which I feel remiss I didn't talk more about, have been incredibly important for the overall picture. Now, El Nino and predicting it is a fantastic question. We can predict El Nino a few months out. Now, El Nino takes a year or almost a year to complete a single event. So a few months predictability is only, it's okay. But we know that we know a lot of things about it, that it's a dynamic connection between the atmosphere and the ocean. It happens when the warm water starts to move west or east across the equator in an El Nino. The convection in the atmosphere actually follows it. And you get these waves which travel along the equator, which carry these signals from west to east. And there's this dynamic process that causes it to kind of play out and then eventually subside. But exactly when they're going to happen, like predicting an El Nino in a year or in 2 years, is something we really can't do. And it may be that there's a certain amount of chaos in the system that prevents a really long-term prediction, much like the weather. You know, if you get more than a week or two out, you really can't predict the weather because it's very sensitive to the initial conditions. It may be that El Nino has something like that in it. It wouldn't be too surprising because it's a similar kind of system, but predicting it in a year from now or 2 years from now is still something that we really can't do. But it's something we still study as well.
And the reason that it goes from east to west or from west to east is because of the Earth rotation?
Actually, it's because of how waves propagate along the equator. So a lot of the dynamics of El Nino have to do with wave propagation. So I mentioned very briefly, for example, that off the equator, signals in the ocean like eddies tend to propagate from east to west. And this has to do with how they interact with the rotation of the Earth and the Coriolis force. Along the equator, you have a zero in the Coriolis force. And in fact, it acts like a waveguide, allowing certain signals to propagate from west to east. So really, it's all about wave propagation, not the kind of surface waves you see at the beach, but waves that are internal to the ocean that happen along density surfaces.
Josh, we have 3 more. Sorry to interrupt you, but we have other questions. So maybe we move to the next question by, okay, Surfuse Ibrahim. So, okay. Okay, you can ask your question now.
Okay, it's a wonderful lesson. My question will be, how can we get bathymetry data of reservoir from this satellite imagery? And if yes, what would be the accuracy? Because I'm from Africa, yeah. Most, like in Africa, we don't have all this data. We have to go to, achieve it through direct observation, which takes longer time to get.
So you're asking about the bathymetry of lakes and reservoirs?
Yes.
So the not exactly. They will tell you about bathymetry in very large bodies of water that are tens or hundreds of kilometers. You can have, like I mentioned, when you have an island, it pulls the gravity literally pulls the water toward the island. If you have an underwater mountain, it can actually pile up the water around the underwater mountain. But detailed bathymetry, like you would need if you were planning to sail a boat through a reservoir, is something that they really can't do because the gravity signal isn't quite that strong. And the radar wave really doesn't penetrate the surface. It really bounces off the surface and comes back. For very shallow, within like 50 meters, I didn't talk about this, but a newer satellite called ISAT has a laser, a green laser, which actually does penetrate 10 to 50, maybe as much as 50 meters of water, and can occasionally measure that kind of shallow bathymetry, which is important to a lot of places. However, that said, the Jason missions and eventually SWOT will tell you about the surface levels of smaller reservoirs, and we expect that to be really important for hydrology around the planet in the future.
Okay.
Thank you. We move to the next question, sorry, by Michael Bacco.
Okay, good evening. Yeah, I'm Michael Bacco from Nigeria, but presently in Germany. I find this lecture very, very interesting. I'm working on a PhD research, and I'm particularly want to develop a marine geoid of Nigerian coastal area using altimetry data. And I know Jason 2, Jason 3 you talk about has limitation, And I know there are crystal SARS Sentinel-3 which replace those limitations. And I'm also aware that SWOT is coming to be a game changer, which we are all expecting. But one thing I want to say is that, like in Africa, particularly in Nigeria, you realize that the tighter gauge data to get this altimetry data limited. So can we use tighter gauge data that are little available, integrated altimetry data to validate the altimetry data? Is it possible? Or another second one again, can the SWOT satellite that is supposed to be a changer, can it give us a data that would not need to undergo any validation?
So yeah, so I think you were asking about comparing with tide gauges. Absolutely. A lot of the validation of altimetry in general has been done for decades by comparison with tide gauges. And there have been efforts to actually use tide gauges in between where the altimeter measures to get a clearer picture of sea level along the coast and currents along the coast. I know in Oregon State, they've done a lot of work like this. There've been a lot of European efforts as well. And for sure, SWOT will increase the amount of data in the coastal area and get a lot finer resolution. But it is important to remember, though, that all of these satellites have return times of 10 days or 20 days. Sometimes you might get data along the coast every 5 days or 3 days if you're looking at many satellites and over a large region of coast. But you'll always, I think, want to have local tide gauge data in addition, because it'll help you see the shorter timescale things. Things like storm surges and king tides that come and go in less than a day or around a day are always going to have trouble being sampled from these satellite missions until we get like a dozen SWOTs, right?
Okay, so the next question by Gilles Someria. So Gilles? Aha, you are muted. Okay, so waiting for Gilles, there is a question by Jérôme. I don't know if I can ask a question to you, George. The question from Jérôme is, will the sum of Sentinel-6 plus SWOT in synergy be greater than the part independently?
I hope so, yes. These are both satellites that are going to provide a lot of new kinds of data for us to look at. The along track SAR from Sentinel-6 is something that will take some time to understand. A lot of the things that traditionally we've kind of taken for granted as problems we've solved in the altimeter community are going to get reopened. Particularly how wind and wave fields affect the measurements. So when you're looking at very fine scales, if you're averaging over 5 or 10 kilometers, you can say, well, we've averaged out the waves and we understand how they affect the altimeter pretty well. But as soon as you start looking at smaller regions, higher resolution along track, higher resolution in SWOT, I think we're going to have our hands full in understanding what the signals are telling us. And of course, we're going to see a whole smaller regime of physics in the ocean that we haven't been able to study yet so far using this particular tool. So yes, I think there's going to be a lot of synergy between Sentinel-6 and SWOT. I think especially because they'll both have this higher resolution data. They'll both be flying at the same time. And so we'll certainly be using one to cross-calibrate and compare with the other for quite a long time in the altimeter community.
Okay, so now Gilles is unmuted. So Gilles, please ask your question, and after
Okay,
that,
thank you.
there will
Okay,
be a
simply,
question. Okay, so please go ahead.
okay. Thank you, Annie. Okay, then I wanted to say that it is a great start for this new seminar series. And I wanted to ask Josh about the differences between the instruments on the Sentinel satellites and the JSON, please. Are there
Yes,
any progress?
absolutely. Yeah, absolutely. So Sentinel-6 has a lot of new toys. And some of my colleagues will, they're not toys, but it has some new features. One of which we've talked a little bit about is this high resolution along track mode. So whenever the radar is flying along, it's not just bouncing a single radar wave off the ocean, it's bouncing many, many waves off the ocean. And in traditional altimetry, what we've always done is just average a bunch of those together over about 1 second, which gives us about 7 kilometers of track. And it gives us a nice accurate measurement. But you can average them together in different ways, which actually try and emphasize the differences in sea level as the satellite flies along. So it has this mode that we call SAR mode, and a long track SAR. And essentially, instead of just averaging all of the data together, you sort of subtract the ones from one side from the other, and it gives you a much higher resolution picture in the along track direction. It's still averaging over a large area across track of 5 kilometers or so, but in the along track direction, you could get down to half a kilometer or several hundred meters perhaps. And we don't really know how well we're going to be able to do that or how accurately we'll be able to do that, but it does give us the possibility of seeing small scale features in the ocean and of getting much closer to the coastlines than we've been able to get with our previous altimeters. Now, in addition, I didn't talk too much about the corrections that get applied to altimetry. But as you look down through the atmosphere, you're looking through the air and you're looking through water in the atmosphere. And both air and water slow down the radar wave as it travels through the atmosphere. We have to correct for that slowdown because it affects the apparent distance between the satellite and the ocean. And we have an additional instrument called a radiometer, which looks at the water through the atmosphere and figures out how much water vapor is in the atmosphere. Now, in the latest altimeter, we've got two new, in the Sentinel-6 missions, we've got two new things on the radiometer. One is a calibrator. The radiometer's stability over time is pretty good, but for doing global sea level, you really want it to be a bit better. So our calibrator will help us maintain the stability of that measurement over the whole life of the mission. And the other is a new channel that actually has a much smaller footprint. So we can do this correction in a 5 or 10 kilometer area of a spot instead of a 25 kilometer spot, which is what we had before. So this was one of the main reasons the altimeter degraded near the coast, was this correction for how much water is in the atmosphere became very difficult as the altimeter got close to the coast. And now it's going to be a whole lot easier. So all those things are new to the altimeter mission with regards to sea level. There's also a new instrument called radio occultation device. This is not a sea level instrument. It looks through the atmosphere at GPS satellites as they eclipse while Sentinel flies around the Earth. And it actually measures the temperature and humidity of the atmosphere as a function of altitude. And this is important for numerical weather prediction and measuring climate change as well. So those are our new toys on the Sentinel-6 mission that have not been on any of the JSON missions so far.
Josh, we have 3 questions in the chat and another one. So I propose you answer the 3 questions in the chat. The last question from the participant Bernard Fuang, and then maybe we close. So can you, there are a lot of questions, another one. So please go ahead, be not too long, maybe. So the first one was by Karina von Schuckman. Do you see it?
Yes. Question on acceleration observed for sea level and concurrent changes in other unusual changes during the past decade, like in the cryosphere, ocean warming. What is your view on the causes for these unusual changes? Well, of course, sea level rise is accelerating. Our cryosphere is melting at an accelerated pace. And as we continue to heat up the planet, the heating isn't happening in a straightforward linear manner. The heating is actually happening faster and faster every decade as well. And so as we increase the pace of change to the entire planet, all of these things are expected to accelerate as well. Sea level rise is accelerating, ice loss is accelerating, changes in the ocean circulation are accelerating. And so we don't actually expect these things to be linear. And in fact, that's one of the really important reasons we need an altimeter that's accurate enough to not just tell us the rate of rise, but the acceleration, because right now that's our best estimate of the next 20 or 30 years. So I think a lot of the stuff that we're seeing now is just happening because the rates of change have increased so remarkably. You know, the global warming of the 90s is not global warming of the 2020s. It's a whole different ballgame.
Okay, so the next one is about the deep
the
conveyor belt.
Yes. Yes, so I didn't talk too much about the overturning circulation of the ocean, but of course the oceans carry heat around the planet, and that's being affected by climate change as well. The overturning circulation is notoriously difficult to measure, but we're just beginning to get a couple decades of overturning circulation measurements that we really can rely on. And so far, it's hard to say whether there's been a slowdown of the overturning, but there is some evidence that in the past 20 or 50 years, it might have been a little bigger. So some of these climate signals and the things like the overturning circulation slowing down and carrying less heat into the North Atlantic are really just beginning to emerge. I think sometime in the next 10 years, we'll really see what's going on with the overturning circulation. It is changing, but is it changing in a way that's big enough and fast enough to say it's caused by global warming and climate change? I think we're still trying to figure that one out.
Okay, the next one is on tipping points for Greenland ice.
Yes, yes. So Greenland has certainly lost an enormous amount of ice. There is some acceleration in the rate of ice loss from Greenland. But what we're noticing, and I didn't talk too much about my other mission, OMG, but what we're finding with our study focused on Greenland is that the ice there is really reacting very strongly to the oceans. The oceans have natural signals in them where they warm up and cool down for a period of a few years or longer. And we're actually beginning to see the ice react to the oceans. So I think a lot of the future of Greenland is tied to the future of the water temperatures around Greenland on the continental shelf. Up on the shelf, the oceanography is very different from in the open ocean. In the open ocean, you have these large gyres moving heat around, speeding up, slowing down. But on the shelf, you have this very interesting situation where you have a layer of warm water at depth and a layer of cold water on top of it, the warm water being deeper because it's saltier and heavier. And so the warm water that makes it up on the shelf is really what's having a big influence on the glaciers around Greenland. And so we need to understand the fate of that warm water, how much it's going to warm, whether more of it will get up on the continental shelf if we really want to predict what's going to happen with Greenland. Some glaciers are probably at the point where they are going to continue to recede and melt indefinitely. And that's what's classically defined as a tipping point. You take away the forcing or the warming, and it continues doing what it's going to do. Some glaciers may be in that situation, but I think we have to learn a lot more about how the oceans are driving ice loss there before we know what Greenland's fate is really going to be.
Okay, so there is another question, and maybe it should be the last one. After that, we will close this lecture. So can you answer?
So I think this is a request for me to sing "Highway to Hell" from AC/DC instead of Elvis.
Okay, so it's not really
I'll put that on my to-do list.
It's not a scientific question.
Yes.
So if there are no more questions from the participants, Josh, I would like to really thank you for this great lecture. It was, as everybody said, it was wonderful. So thanks very much. And I would like to advertise the participants that next week we will have another online lecture in the same series. It will be given by Guy Brasseur, and it will be about air pollution as measured by from space, in particular by the Sentinel-5P satellite. And I would like to let you know also that each week of February there will be a lecture, and there will be one on land ice, Greenland, Arctic land ice. I don't remember the whole program, but you will see the program on the EC website for the weeks of February. And next week it will be on Thursday, but instead of